we're going to our next keynote speakers, and it's Sakshay Mahna. Sakshay is a robotics software engineer and research intern at Art Park.
Yes, and Sakshay is going to talk about path planning algorithms for ROS. We are going to learn with him how to implement path planning algorithms as plugins for ROS navigation stack. And then we are going to learn how to visualize their results on RBase. Hello, Sakshay, are you ready?
Yes.
Perfect.
Okay.
Then the audience is all yours.
Have fun.
All right. Thank you. Okay. Hello, ROS developers. I am Sakshay, and as told, I was a final year student at IIT Ropar. I have completed my degree, and apart from my studies, I have a YouTube channel, Robotics with Sakshay. And the content of this talk comes from the backend work that I did for one of my playlists, motion planning for robots. So in this talk, we are going to discuss some of the motion planning algorithms that exist, and we are going to implement them in ROS. By the end of this talk, you would be able to tell or explain how motion planning algorithms work, differentiate between different types of motion planning algorithms, and even implement your own algorithms on a mobile robot. So as we can see, we are going to use a TurtleBot 3 robot for the same. So let's start and let's see how many algorithms that we can cover. Okay, going on, the first step is to launch the simulation. And for that, we will open the shell and type or copy this command, ROS launch. So this is going to start our simulation. And okay. Now, the original or usual way of writing path planning algorithms is in ROS is to write them in C++. So when we want to add a new global path planner or want to write one, we have to create a C++ based plugin in ROS. And we have to use the base global planner interface to do so. But in this talk, we are going to write these algorithms in Python. And we are going to use some base packages on top of which we are going to build our this Python based algorithm writing section. Okay. So the base packages, so the overall idea behind how the complete software is working is that we have this SRV client plugin package. So once the navigation node is running in the background, navigation node is going to query the SRV client plugin with the start location, the destination, and the different cost map parameters. The SRV client plugin is then in turn going to send the parameters to the global path planning plugin, path planning package, which is written in Python. And then in Python, we are going to write our own logic or whatever algorithm that we want. And then we are going to send the complete path that we developed to the SRV client plugin. And then in turn, it is going to return it to the navigation package, navigation node that we are running. So that's the overall picture that is running. We are not going to write any C++ code. We are going to use the base packages as it is, but we are going to write algorithms in Python as it is the main title of our talk. So first, we are going to write a very basic or naive path planner, which is the random path planner, to demonstrate how we can write algorithms like this. So the how this random path planner works is that we are going when the robot is at a current state, we are going to get its neighboring states and randomly select one of its neighboring states. And once it is selected, we are going to move the robot to that state. Once in this new state, we are again going to get the neighbors and randomly keep on selecting the nodes or the states in which the robot is going to be in. So that's the overall picture. Now we are going to write our algorithms. So we need our code editor. We are going to open that. So it will take a while to load. So all the algorithms that we are going to write go in this directory: home user, catkin workspace, src, and scripts algorithms. Now we will be writing a planner from scratch, which is the random path planner. So let's wait while it's loading. Okay, so while it is loading, I'm just minimize this. So in the next cells that we can see, we are going to copy and paste the code from the notebook to the code editor that we have. So that is going to be the complete process. So in the navigation of the code editor, we are going to go to Catkin workspace, SRC, global path planning, scripts, and in the algorithms folder. Here we are going to where we are currently having all the algorithms that we are going to run in this complete talk. So right now we want to create a new file called planner.py, but we already have this, so we are going to delete it so that we can write it from scratch. We'll just delete this one. And then on the algorithms folder, we're going to right click and create a new file, planner.py. So the first step is to copy or import the required libraries. We are going to use the random library since this is a random path planner. Next, we need to create a function for the planner. Let's copy this first. So over here in the planner, we can see certain parameters that have been listed like start index, goal index, width, height, cost map, resolution, origin, grid width. All these are required when we are also writing our own path planners as well. These are going to remain constant for all the algorithms that we are going to write. After that, we have initialized variables, open list, closed list, parents, and so on. Open list will contain the node from which we are going to sample the nodes. Closed list contains the nodes which we have already explored. And parent is going to help us to recreate the path that we have calculated from goal to the start. Okay, so we have these variables. Now we need to copy the code in the next cell. So since this is Python, we need to take care of the indentation. One thing that we can do is to copy the complete cell, and then we are going to have our cursor at the complete left of the editor, and then we are going to click paste. This is automatically going to take care of all the indentation problem that we would have faced as such. Okay, now in this code, what we are doing is keep running in a loop and selecting the elements from the open list randomly. And we are putting them in the closed list and then getting their neighbors using this find neighbors function. We are going to write this later on in the code. And then again, adding those neighbors to the open list. That's what we are doing. Another important thing to take care of here is that we are using this grid width set color function. This is important for the ROS visualization that we are going to see for each of the algorithms that we will see. Now, what this means is that whenever we are going to explore a given state or a cell, the color is going to turn yellow so that we can visualize that the robot brain has explored that state. Okay. Now, once again, to take care of the indentation, we are going to place a cursor on the left over here and completely copy the code in the cell. Yes. In this part of the code, we are just recreating the path from the goal to the start. That's all here is. And we have completed the function planner, that the algorithm planner. Now we are going to copy this find neighbors function. This is a bit large, so we are going to we'll just copy everything and paste it in the same file. Once again, the cursor should be in the complete left. So we have our find neighbors code, which is being used in our planner code as such. Find neighbors is going to use some mathematical functions to find the neighbors of the current state of the robot. You can read this on your own as well. It's quite simple to understand. It's just avoiding the states that already have obstacles present on them so that the robot does not collide. Okay, so we have our code ready and we have saved it as well. Okay, it's saved as well. So to run the algorithm, we need to open the algorithm.py file, which is present in the algorithms folder. So here we have this file. And in this, we are first going to import the planner file that we wrote from .planner import planner. And in the part over here that says algorithm goes here, we are going to replace this with the planner function that we just wrote. So this is saved as well. Now we need to run the code. We have this simulation already running. We'll just zoom it a bit so that we can see it clearly. Okay. So to run the code, we are going to open a new shell terminal. And we need to give the execution permission to the one of the files that we're going to use. So we will just copy this command chmod +x/home to give the execution permission. That is done. Now we are going to start the server using the command that are given over here. ROS launch, global path planning, and turtlebot3 rosworld.launch. This will automatically start the navigation server that we discussed, the Python one, and the RWiz window that we have. So we can give the destination to the robot where it has to go. I will the size as well. So in the window, we are going to click the maximize button over here as well. So since this is a random path planner, we don't know how much time it is going to take to execute this. Therefore, I will give a very close destination so that we can see that the algorithm is working. So we're going to select the 2D nav goal button over here and give a very close goal. Let's say over here. So this is the destination, and the yellow ones are the random path that the robot is generating. So once the robot logic or brain reaches the red dot that we can see over here, the robot will have completed the path planning and start following the path. So it has reached and it is going towards the path that we have just generated. So this is the random path planner. Now we will try out some interesting algorithms that actually are very efficient and used in the robotics literature as such. So the first thing that we will do is to close the RWiz window or the other terminal that we had running, and I'll close this window as well. Okay. So there is some additional code as well that I have provided in the notebook so that it helps to write other algorithms as well, apart from the ones that we're going to discuss in this talk. Okay, so the first type of algorithm we are going to discuss are grid-based path planning. These are the most common ones, and these usually work on a graph structure. A graph is a mathematical structure that represents relation between entities. So there are two graphs consist of two basic things, which are nodes and edges. The nodes represent the entities and edges between them represent the connection between them. Graphs are almost everywhere present in the world. If we see the social media graph, the nodes can be the people and the edges can be the relation between them. They can either be friends or they can either be enemies and so on. The graphs can also be seen in road networks where the nodes are the intersections or landmarks and edges are the road connecting these intersections or landmarks. Internet can also be seen as a graph where the nodes are the websites and the edges are the websites connected through hyperlinks. So how we are applying this graph structure to our robot path planning problem is, I'll maximize this. So we have this map over here, which our robot is currently present in. So first, we are going to create a lattice out of this map by simply drawing horizontal and vertical lines. Wherever the intersection occurs, we are going to call that a node. Now, for each node, we can see that we have 4 edges: up, left, down, and right. So each node in this graph has 4 edges. This means that if the robot is currently present in one of these nodes, it can move to either of the 4 nodes in its neighborhood. We can also extend this relationship by including 8 neighbors, that is top left, top right, and bottom left as well. We have used the 8 neighbor model, but for demonstration, I have included this diagram of the 4 neighbor one. So how this algorithm now works, let us see how these graph-based algorithms work. So first we have been given start and the goal node. The first step that we have to do is expand the graph. So we find the neighbors of the start node and expand the graph. We use a function f, which is a distance metric function. A distance metric, if you have studied in mathematics as well, distance metric can be Euclidean distance or even Manhattan distance and so on. It just measures the distance of how far a robot is from its goal and so on. If we consider it in more detail, then the function f is what is going to create different types of graph-based path planning algorithms. If we change the function f, then we are going to have a completely different path planning algorithm. So that is how it is. So once we have expanded over the neighbors, we calculate the function f for each of these nodes. And let's say we get 1, 2, and 3 respectively for the nodes 1, 2, and 3. Now we are going to select either the minimum or the usually we choose the minimum f function, but in some cases we can also have the maximum. We are going to choose the minimum f function, and then we are going to expand this just like we expanded the start node. So we have the first node expanded into 4 and 5, and then we are also going to calculate the f function for these as well. So we have 1.5 and 5. Once again, we are going to take these 4 values and calculate the minimum and expand over that again. So we can see 1.5 was the minimum and we expanded over that. So we get 6. Now f of 6 is equal to 6. Now in the next step, we have the minimum, which is f of 2 equals 2. So 2 is going to be expanded. So in this way, we will just keep on expanding the different nodes until we reach the goal node. And once we have reached the goal node, we are going to use our parent dictionary that we saw before to recreate the path from the start to the goal. So A-star algorithm is the one we are going to discuss in these graph-based algorithms. A-star algorithm, as I told as before as well, that the f function dictates what path planning algorithm we are going to get. So let's say that, so in this case, the f function is a summation of 2 other functions, which are g of n and h of n. So g of n is the actual cost that it takes for the robot to reach the node n from the start. And h of n is the estimate of how much distance the robot has to cover from node n to reach the goal. So the g of n function is quite easy to calculate. We can simply count the number of steps the robot has taken. That is going to give us the actual cost. H of n is a bit little bit tricky. Since we need an estimate, we can simply take the straight line distance between the node n and the goal. And this straight line distance, also called the Euclidean distance, usually works really well for the A-star algorithm. And we have used that in our algorithm as well. Okay, now let's minimize this and run the A-star algorithm. So once again, we have to open the algorithm.py file and change the planner function that we were using to A-star, so that the robot brain can use the A-star algorithm. So we have set the A-star and now we need to run the server again. So let's do that. Okay. Once again, we will copy the command over here and paste. Okay. Now, we will not be referring the simulation so much because the visualizations are important in ROS as such. Now, since A-star is a very optimal and efficient algorithm, it's going to straight away find a path from the start to the destination that we give. Let's say that the destination we give is over here. So it's very quickly going to just go in the direction of the destination that we have. That's why it is one of the most efficient and mostly used algorithm in robotics and other fields as well. Okay, so this, okay. Maybe this path is in the obstacle cost map as such. That is why it is not able to expand over this red dot. So we're going to run this algorithm again with another destination input. Let's give it a little closer one, not in the obstacle range. So once it has reached the destination, the robot starts and moves towards the destination that we have given. And this is the A star algorithm in action. Usually we study this in theory, but this is the implementation in simulation that we can see along with visualization. Okay, now let's close this server and move on to the next algorithm, which is sampling based algorithms. So in A star or the graph based algorithms, the problem is that we are going over each and every node and checking it whether it and calculating the function f. Let's say if our problem consists of not 2D motion planning but 3D motion planning in the cases of drones or mobile robot or robot arms, then the search space is going to increase very drastically and we will not be able to check each and every node. Hence, we need to explore any other different ways so that we can approach this path planning problem. Now, our problem is not to find the shortest path, but to find the path in the minimum amount of time so that the robot does not keep on waiting until it will get a path so that it can follow. So sampling based algorithms, what they do, instead of going over all the nodes in the graph, they randomly sample points from the space or from the map and construct a new graph on the sample points. Then we can run any other graph planning algorithm to generate a path that the robot can follow. For example, let's say that we have a start node over here and our goal node, and we have two obstacles, C1 and C2, that the robot has to avoid. So the first step is to sample the points randomly in this environment, and then we construct a graph using these as nodes. So once this graph is constructed, we can run any path planning algorithm, the graph based one that we discussed before as well, to find the shortest path through this reduced graph that we have. That's how sampling based algorithms work. RRT, or rapidly exploring random trees, are one such sampling based algorithms which are quite popular. There are other variants of RRT as well, but we're going to discuss the simple RRT over here. So what they do, instead of having different functions for generating the graph and for sampling the points, they do the RRT algorithm does both of these tasks simultaneously. So it is going to generate a random point and it is going to connect this random point with the nearest point in the graph that we currently have. So once we have this random point, since start is our only graph, we are going to connect this to the start node. Next sample random point comes over here and we are going to connect this to the nearest node that we have, which is this node. Similarly, now sampling, as we can see, the nearest node is the middle one over here. That's why this node is connected to the, this new node is connected to the middle node over here. And in this way, this procedure keeps on going until we reach the goal. There are some certain tricks that are applied to reduce the randomness a bit so that the robot eventually finds the path to the goal. Because of this random nature, there may be some events where the robot is not able to reach the goal. Therefore, we also include some certain tricks which can be used in the coding of this algorithm. So now let us run this algorithm again. This step is once again the same. We are going to change the A star over here to RRT. And we're going to save this. It is saved. And now we're going to run the previous command again. So let's try giving the goal over here and let's see if it reaches in time. So as we can see, it is randomly sampling the point. Oh, yeah. It is randomly sampling the points, and in quite a short amount of time, it reached the destination. The major reason because of this is the parameters that we have set. Let's run this, try running this again and see. The speed of this algorithm depends on the parameters that we have set. If the randomness parameter is low, then the robot is going to reach the destination quickly. Otherwise, it's going to create a very large graph and take a lot of time to reach the destination, as we can see in this case. That the randomness does not allow the robot to reach it quite quickly, as we saw in the previous example. So it has reached and it will follow the path and reach the destination. Okay, we'll close this. Now we're going to go to the next path planning algorithm, which are learning based path planning algorithms. And for that, we need another simulation. We are not going to use this simulation. So we need to close the simulation as well. So first, let us run the simulation, and then we will discuss what does it mean to use learning based algorithms in path planning. So for the simulation, the command is given in going down, and we're going to paste the meantime. Okay. Okay. So the name of the package was Q Learning instead of Q Learning World. So that's why the error was coming up. Okay, so we will have it will launch our simulation and we can discuss what does it mean to use learning based algorithms. So learning based algorithms are quite popular these days, and reinforcement learning is one such very popular algorithm class that are used nowadays. And the major reason for their popularity is due to the advent of deep learning. But for our algorithm over here, we are not going to use deep learning. We are going to use a simple reinforcement learning algorithm without the use of deep learning. So reinforcement learning is the paradigm of machine learning in which a robot learns by taking actions in the environment. And based on that, it decides whether that action was good or not, and learns that next time it should perform that action or it should not perform that action. And this feedback is given by what is called a reward. So if the robot does something good, it will be rewarded with positive points. It will be encouraged to do that, to take that action again. If the robot does something bad, it is rewarded with negative points, in discouraging the robot from taking that action next time again. So the main goal of these algorithms is to learn a policy. In simple words, a policy is simply a sequence of action or a set of actions that a robot can take. So that, it is a sequence of actions that a robot can take. And the main goal of these algorithms is to learn such a policy or a sequence of actions that will maximize the reward of the robot. That is what we are doing. Some examples of where this is applied apart from robotics is in stock market, where we have to set up a sequence of buys and sells so that we can maximize the profit, or even in digital marketing, where we should place the ads so that the revenue is maximized. And in video games also, like the OpenAI and DeepMind that we usually see on the news, the sequence of actions so that the score of the player is maximized. So how are we applying this Q learning algorithm for our robot path planning? So since if we have a goal start node and a destination node, then we need to find a sequence of actions that the robot can take to start from the start node and reach the goal node. And we need a reward to do that. The reward is going to be the distance of the robot from the goal. That is going to act as the reward for the robot over here. Now in this case, the reward, we would like to minimize the reward. So to change this problem to the maximization, we will simply return the negative of the reward. This is going to turn the problem of minimizing to maximizing. That is what we do. Now we have a specific algorithm in the reinforcement learning algorithms list called Q-learning. So what Q-learning is, that we have to try and learn what is called a Q table. A Q table is simply a table containing states and action pairs. So let's say that we are currently in this bottom left bottom left state, and we have the actions either move up or move right. So we are going to have two pairs of this, the green state with up action and the green state with the right action. And we are going to have this similar action y action and state pairs for all these states in this Q table, in this grid. So for each of the state and action pair, we are going to map this to the reward. What this means is that the Q value represents how much beneficial it is for the robot in a given state to take an action. If the robot is in the green state and it takes a right action, then how much reward it will be getting in the current and the future combined. If the robot is in the current green state and it takes an action up, then how much reward it will be getting currently and in the future. So based on that, the robot will try to maximize the reward it will be getting for each action it takes in each state. So that's what is a Q table. Now the problem over here is that we need to learn this Q table. And to learn this Q table, we have this very complicated mathematical expression. I will not go over this as this is not beyond the scope of this talk, but it's completely mathematical. And in the code, we also apply this mathematical function to learn the Q values. Now, one way to learn the set of Q values is that we iterate over all the state and action pairs and use this equation to generate the Q values. But this looks like a quite unnatural way, and if the states and actions are quite large in number, then it will be difficult to take up this method. Hence, a more natural way for the robot would be that we tell the robot to take any action, and based on that, it will update the Q table. And that is what we do. We use what is called an epsilon greedy policy. What this means is that with some probability, the robot is going to take a random action, and with some probability, 1 minus epsilon, the robot is going to take an action based on the currently learned Q values. So that's how the Q learning is going to happen. Once this learning phase is complete, the epsilon greedy policy, we are going to remove that, and we are simply going to tell the robot to follow the Q table or the Q values. And this is the complete procedure that is written in the code as well. So let's run this code and see this in action. So we have the first step is to once again change the algorithm over here in the algorithm file, and we're going to select Q learning. So it is saved, and then we are going to run this again, the path planning server that we had. Okay. Yes, the simulation is running. Let's open it over here. Okay. Now we are running the path planning server. So a bit small problem with this algorithm is that due to the computation, we cannot give very large paths with this robot. We have to give only certain small paths, not that very large, but small to medium sized paths. So let's say that we give it a path over here. So this is the grid that it has generated. And once it has learned the Q values, it is going to output that as well. let's see. So this is the policy that it learned, that it has to go up and then it has to move to the right. And the robot has exactly followed that policy that it derived from the Q table or the Q values. It first went up and went to the right. As we can see, for each state, we have an action that we can take, which is going to maximize the reward, which is for each state, the robot is told to go up. So if by mistake the robot is lost in this complete state map, then the robot knows at each state what action it can take to reach the goal. So that is the different thing about these learning algorithms, that it has learned the every possibility to the uh, path planning problem. Right. Okay, so we have discussed all the three algorithms that we had to discuss for this talk. And overall, the conclusion over here is that through this session or notebook or talk, we have understood what are some basic motion planning algorithms, the three types: grid-based, sampling-based, and learning-based, and how we can implement these path planning algorithms in Python. So if uh, you want to check out the code, we can also check out the code. The notebook and the ROS will be available. And if there are any questions, please do let me know.
Okay, thanks, Sakshay. Very nice presentation.
Thank you.
Great, very interesting.
And also very clear.
Yeah. So, as always, Q&A section. You have their Q&A section just below side of the chat, and there you can post all your questions and also vote for the ones that you find more interesting.
Yes, and let me tell you that, Sakshay, that we already have some questions already posted while you were talking, so it has generated some excitement on the audience. So let me go with the first one for you. So it's from Rodrigo Gonzalez that says, what is your thought process when deciding which algorithm to implement in a robot? What would be? How would you select one algorithm or another?
Yes. So this is an interesting question because a lot of people have this doubt. It depends on the environment or the problem statement that we have. If we want the robot to do path planning in the minimum amount of time, then there are going to be RRT like algorithms that we're going to use. If we want the robot to find paths in the shortest amount of time, then there are different algorithms to use. If we want the robot to avoid the obstacles better, then there are different kind of algorithms. So it depends on the problem statement that we have, like what the robot is supposed to accomplish. And based on that, we select the algorithm.
So it's not one algorithm fits all.
Yes.
Okay, let's go with another question.
Yeah, one from Marcos Vinicius that says, using RRT, different from deterministic algorithms like A star or Distra, don't you use the H cost, distance to the goal, to build the cost function? In addition, which tricks do you use in RRT to reach the goal as you have mentioned?
Okay, so the tricks that we use for the RRT algorithm is that we do use some form of estimation to the goal. Like we calculate the distance or the vector from the start to the goal, and we try to direct the nodes towards that vector. So that is one trick that we use. It is slightly like it is similar to the heuristic or estimate that we are using, but the complete algorithm is different as we are using randomness over here compared to completely deterministic things.
Okay. Hope that answers your question, Marcos Vinicius.
And there is another one from him.
Yeah. Marcos Vinicius also says, as far as I understood in Q-learning, the policy is to respect the robot's constraints, kinematics, acceleration, limits, and so on, because it has not chosen any shortest path, diagonal, for example. Why doesn't it do a diagonal, for example?
Okay. Right. So the for the first part, the policy that like for this we can set the Q learning algorithm to any particular configuration that we want. But for this example, this was mostly a demonstration example. So over here, the metric that I have used is the distance to the goal. So it is trying to minimize the distance. And why it has not chosen the optimal or the diagonal path is because I have not set the eight neighbor model that we discussed before. So it only knows that its neighbors are either up or left, right, or down. It doesn't know that it has any neighbor top left, top right, bottom left, bottom right. So that's why it is not choosing one of those.
Makes total sense. Makes total sense.
Yes, and then let me ask you another question here from Maladi Naga that says, are there any specific websites that we can refer to know more about the algorithms and path planners that we can use in a robot?
Yes, there are a lot of reference websites. Like, I think I will post the link in the chat later because there are a lot of links, and Google, like Google searching on Google is the best resource that we have. So I'll link some of these in the chats. Like there are some good presentations from Carnegie Mellon University as well, which have a complete course on path planning. So that is a very good reference.
Okay.
Okay, one more question.
Yes. Well, actually, yes, I have a question, but here there is Lucas Macha that says, go Google. In answer to the question of this. Yes, but I mean, so everybody can ask any question here. There is no bad question or wrong question.
Sure.
Is in order to facilitate. So because Sakshay, he has already distilled the knowledge, so if he can help us with his experience on going faster into the proper websites and so on. I presume that was the question from Maladi. And then one question from my side I would like to know is how difficult do you think that it could be to translate those plugins from ROS1, because you have been working on ROS1, into ROS2? Do you have any idea about this?
So I did study it a little bit. In just like we have in ROS1, we used like I discussed before, that we used a base like a parent planner plugin that we inherited, and we created our C++ code. There is a very similar kind of thing in ROS2 as well, where we can create our own path planning plugins in C++. There is like a little bit difference in what the function names are and how we do the things, but the process would remain almost the same. We have to write that C++ code and interface that with Python and write the code in Python.
Yes, and just interface with a new plugin structure in ROS2, but the rest of the code will be the same, right?
Yes, because there are not many differences like in my code as such in Python 2 and Python 3. So Python code remains same. C++ will change a bit.
Okay.
Okay, so that's it for the questions. So thanks a lot, Sakshay. And
thank you.
Thank you. So now remember that it will appear a tiny box there where you can rate the speaker, and at the end of the conference we will say who is the best speaker 2022.
Exactly, of the conference. And now we are going to switch to the next speaker. So before we switch to actually it's not a speaker, it's different, it's a talk. So it's a talk made by one of our colleagues he's going to talk about the new features in ROS2 Humble. But before going into that, remember that this talk also has a project. So you can go now to the Docs tab and click there in order to get the project for the next talk after you have voted. And now
what we're going to do is another quiz.
Yes.
So this quiz is sponsored by Corelix, company leader in service robots based on ROS. And the one that answers the question first, it will win. What will it win?
One T-shirt of the conference.
And a super mug for your coffee and other
ROS Dev Days in the deep sea. Yes. Great. And how can you win this? Well, we are going to show you now one video in the meantime that we are changing the speaker. So you can watch this video and you will see a lot of information there about Corelix. You have to take notes. And then at the end of the video, there will be a question. The first person that answers the question, then it will win the t-shirt and the mug.
And the mug. Yeah, so...
But don't do tricks, okay?
No, no tricks.
Don't do tricks, okay?
We will see it. We will see it.
Yeah, we are watching.
So, see you in 5 minutes then. And welcome back. So the winner is Mayank Joneja. So Karelik's cloud was the solution.
Correct.
Yeah. So congratulations. You'll get t-shirt and mug. Congratulations.